Well, good morning and welcome to the webinar of the week at Easy Power. This week we're going to be talking about motor starting, part one, and this is Chris Duffy. And so we're going to be going over beginning aspects of starting induction motors on your system in a dynamic method, and we're also going to be looking at how to perform parameter derivation so that we can get the greatest amount of detail that we can when performing motor starting. That's one of the things that we elected to do from the very beginning, is we elected to create a motor model for transient motor starting and for dynamic stability that would give us the greatest amount of detail without having to worry about it. And I have some slides to those points that I'll go over in a few minutes. But what I'd like to do now is go ahead and perform a quick motor start for you and show how quick and easy it is to do a motor start in Easy Power using some of the data that's in the library. So let me move this over and bring up Easy Power. I've got the bigger case loaded, and if you go down to switchgear 13, excuse me, in bigger, you'll see that we have a 3,000 horsepower motor on this bus. It's a 4160 volt bus. And what I want to do is perform a motor start with this. This is my case. I've built it. It's got all my components in my system, maybe all my protection built into it, and all I want to do is start a motor, but I haven't gone to the effort of putting in any dynamic stability data. So, well, why don't we start first by going right into stability without actually putting in any data? I think you'd find that an interesting capability of the stability package. You don't need any data. It's just going to model Thevenin equivalence, and all your loads on your system is constant impedance. But it's amazing the number of different things you might be able to do later on it. I hope to mention a few of those near the end of our presentation. So if we enter dynamic stability, notice that it pulls up the case over here on the left, and it's solved. It's actually a solved power flow case. And that is mandatory and necessary for running any type of dynamics or transient motor starting, is you need to know the initial condition of your system based off of a power flow simulation. On the right, we have our plot window, and in the bottom here, we have what's called the message log, and I'll go over each of these as we progress. But now to do a quick motor start, without any data at all, let's consider possibly starting this without any data. What would happen? Now, we'll learn some things about breakers as we talk here. And the first thing to learn is that when you're in stability focus, and if you want to open and close a breaker and resolve the initial condition before you do a motor start, the way you do that is you right-click on the breaker, you say open and resolve. So now the motor is offline and prepared for us to start it. If it's online, we can't start it. It's already there. So we have to remove it from service and then start it dynamically. Now, the way we would start it is by double-clicking on the breaker. Just like in short circuit or power flow, if you open and close a breaker, everything is resolved again and redisplayed for you automatically. Likewise, in dynamic stability, when we do double-click actions, we get a similar but slightly different behavior because everything's real-time simulation now. So what it's going to do is run for us. I'll show you this in the actual dynamic stability options, but it's going to run for a second, then it's going to start the motor, which of course has no information about starting current or any inrush conditions or anything, and it's going to literally just throw the load of the motor back on at 1 second and then run for 6 seconds. So if we blow this plot up, notice that it's exactly what we have. We have no dynamics information. We see no rounded curves or anything because all we did was run steady state for 1 second and then throw the load of the motor back on, and we step up into that condition and continue on. So we went from off-load to an on-load condition. And so you can do any of these type of switching actions inside the dynamic stability focus without adding any dynamic stability data at all in any of your equipment. So, well, let's say we actually wanted to do a motor start here. I mean, a real one where we see a dynamic response. So I'm going to reset the simulation. Whenever you're done and it's finished plotting and you want to perform another simulation in dynamics, you click on the reset. So we reset, and now I want to return to the database focus. I'm going to say no because I want to undo this switching action that I did. And now I'm going to double click on the motor, and notice it's 4 kV motor, 3,000 horsepower, power factor efficiency. And if I go to the stability tab, which is probably a place few people have gone who are attending this, you want to enable the motor where you can now get a dynamic behavior out of the motor. Notice some things that are going on here. We have no information here for the starting load, running load, and these red hashes mean we don't have anything. Well, given we don't know how to fill in this information necessarily, do you know what the armature resistance, armature inductance, L, X, X prime, X double prime, T prime 0, those are parameters that we hear about when we talk about synchronous generators and getting generator data sheets. So it's kind of odd that these are what we need. But again, we're putting together a fully detailed flux model. So to get running quick, let's go to, let's see, this is a medium voltage motor. So I'm going to go to the Siemens data because I know there's medium voltage data in there. And the largest one I have here is a 2250 horsepower motor, 1800 RPM. Now I've selected it, but I haven't loaded it in here into the data. And to load it in, I just click on the library button. This is very similar to other locations in EasyPower where you bring stuff in from the library. So we click on the lib and we get a message. All right, overwrite the power factor inefficiency. Now, in this case, I want this motor to be the motor. You know, I want this motor to be exactly what's in the library. I want it to be completely consistent, specification tab, and also the dynamic stability data. I want them to mesh. So I'm going to say yes in this case. Later on, when we're doing a parameter derivation, we're going to say no, and I'll tell you the reasons why we do that then. But for now, if you want a motor out of the library, let's say you put one in the library yourself, and you want that exact motor to be at that location, then you say yes, overwrite the power factor inefficiency. Now let's complete our task here by selecting a generic speed squared, loading it in, generic speed squared, and loading it in. And this type of a load model allows the torque on the shaft to be presented in a squared relationship, so that when you're at 0 speed, you have 0. When you're at 100% speed, you get 1. So 1 squared is 1. And when you're at 50% speed, you'll only have 25% of the torque on the shaft. So it's a speed squared characteristic. Likewise, if you use speed cubed, you'd have that same relationship holding, except for it'd be a cubic relationship. So this automatically loads the motor with speed. You don't have to put in a torque speed curve. Now we have that capability, and we'll discuss that later as well, of actually being able to specify a digitized torque versus speed curve. But for now, just to get a start going, let's choose these loads. Now you notice right away that the symbol changes on the motor. And this is an option that you can disable if you'd like not to see it on the one line, but when you get EasyPower, the installation, by default, if you have dynamic stability data, you will get a rotor symbol on the inside of the induction motor. And now let's proceed to the dynamic stability focus, where again, we have a solved pre-simulation power flow condition. But it's online, obviously, right? You can see the load that's here, and our motor is online. And so what we need to do is we need to open the breaker, resolve for this precondition, right? And now we're going to start by performing the double click. And automatically we get a motor start simulation for us. All the dynamic stability data was there to be able to do it. Now, one of the intelligent features that is built into transient motor starting and stability is the auto plot capability. When you close, let me go back here. when you close a breaker on a motor, it notes that you're on the motor. It knows what it's connected to. And it knows that, oh, this is a motor. Why don't I monitor automatically the terminal voltage of the motor, the current in the motor, the speed of the motor, and the electrical air gap torque. And those are plotted for you here. And we can see that in this motor starting that we have current of somewhere around 5.1785 per unit. Notice I'm getting that here from this this plot, or this little data tool that I can drag over the data cursor here. It's this option here. You can turn it off, turn it on. And the red line is showing us about 5.3 per unit current. The voltage is dipping down to around 84.5%. Very interesting. And our torque at starting is somewhere around 60% on the purple. So we've had a nice motor start simulation done here. And let's see, it's taking about, it starts at 1 second here and goes 3. So that's a 2-second start roughly. All right. Now, a couple details about the breakers for you. Let's go back to this breaker switching again, because this is how you're going to be doing most of your motor starting for single motor starts. If you want to do a whole a simulation where you're putting several motors online over time, you're going to have to write a script for that, and we'll talk about that in a later webinar. But for now, the breaker actions are really what you're going to use. So let's say just by chance this motor didn't start within 6 seconds, and we needed to lengthen our simulation. Well, the way you would do that is by going to the dynamic stability options under the double-click control. And here we let you specify for a given action how long you want the simulation to run and how long you want to delay it before you actually perform the switching action that you selected. There's a couple other things here for dynamic stability. And let's pay most attention to these two items right here. Breaker or switch to open and breaker or switch to close. All right, so default values, simulation end time is going to be 6 seconds and the delay time is 1 second. Again, you can change these if you want. The delay time is how long it runs steady state before it actually closes or opens the breaker or switch, and this is the total runtime length. Now, you may say, well, why would I ever want to delay? It gives you a nice indication of the pre-switching condition, and it also proves out, or maybe doesn't prove out, that you're running steady state. Oftentimes when we have large systems that have significant numbers of generators in them, and they have excitation systems, if they ever are initialized on a limit, which could happen if your power flow case, for instance, was putting out too many VARs above the actual limits on the inside of the AVR, not necessarily in the power flow limits. What would happen is as soon as you started to run, it would start to move. It would automatically start to say, hey, I'm on a limit, I need to get off my limit. And it would start to react. Well, you kind of want to know that before you run a simulation. You want to make sure that you are running steady state. And the way I've elected to do this is by default in all of the double click controls. I've let it have a delay time of 1 second. And so you'll see that here, if we run this again, that we waited 1 second before we actually started the motor. And so that's done on purpose. Again, if you want to change it, if you don't like to see it, that's fine. Another thing to point out here is in the plot for the terminal voltage on the motor, notice that it is 0 and then comes up to its starting value and then its recovery value after the motor has gone past the knee of its starting curve. It's not the pre-start condition. And that's actually correct because we're not plotting the bus voltage here. We're plotting the voltage on the motor. So the motor voltage is 0 before it starts, and then when it closes in, then it dips down to this voltage of around 86%. If we wanted to see the voltage pre, during, and post for the motor, all we would have to do is plot that particular voltage if we wanted to see it. And we can do that very quickly in the define plots. We click on the define plots button in the ribbon. And the quickest way to do it is to first select the row that you want to begin in. And so we're doing the first item in this row. And then you right click on the bus and say plot bus voltage. Notice that you can, while this dialog is up, you can pan and zoom in and out to choose other things to monitor. So you don't have to look at just this bus voltage if you don't want to. In fact, why don't we also look at one that's up here? There we go. Now we have 2 bus voltages in our plot. Hit the OK button, reset, and then run the simulation again. And in plot 1, we now have 2 bus voltage plots. This is switchgear 13, and this is bus 3. Switchgear 13 is on our 4160 volt bus here. And if we take a look at it, we see that the voltage indeed dipped down to that value here. Excuse me, let me move this out of the way so we can see it. Bus 3 is above. Here's our switchgear 13. And so we got down again to our 81% voltage here on switchgear 13. So there you go. If you actually want to see the before, during, and after bus voltage plot, just select it and plot it with the plotting tool. And again, there's many more things you can plot, many more things you can select. If you're over here and you in the define plots window, click on that. Notice all the things that you can look at for the motor as well. If you want to look at flow in the transformer, again, things that you can look at during a simulation. So there's a quick run through a motor start for you and how to get some plots up, how to look at the result of your motor start. And what I'd like to do now is move into a few slides to discuss and move us through some beginning aspects, a little bit of documentation for you, and then looking at an actual parameter derivation to prepare us for a motor start of our own motor, not just one that comes out of the library. Okay, so let's move to these slides. Now, this is the form that our model is going to be in the Easy Power software. We have a network model on the right-hand side. We have a Thevenin internal impedance, and we have a Thevenin internal voltage that drives the network with our induction motor model. Now notice something, that this is literally almost a standalone model and interacts only through this terminal voltage connection, through this Thevenin equivalent. All of the details of the induction motor model are here on this side of the network. The network is solved on every single time step as the Thevenin voltage is updated. This motor updates itself based on the current, the terminal current conditions of the network. Also, there's an interaction of the induction motor model with its load through speed being supplied here to the load and the mechanical torque being supplied to the induction motor model. Now, the loads we discussed were speed squared, speed cubed, and also the digitized function of torque versus speed curve, which you can do. We're not going to do that today, but again, if you have your own loading curve, if you actually have one, definitely put it in there. Don't use speed squared or speed cubed standard unless you know that's their characteristic. Definitely put in a digitized function if you can. The most commonly known model for an induction motor is the double cage circuit model. It's a steady state circuit model. It's not really a transient model. It does the double cage simulation. Its circuit computations involve complex numbers or phasors, and you model the power draw through R1 and R2 resistances as they are divided by slip in those legs of the branch. And the form of that model is here. And of course, I'm sure you've seen this before, if not in school. You've probably seen it in papers documented repeatedly. This model has armature, resistance, and reactance. This is the magnetizing impedance, similar to magnetizing impedance of a transformer. And these are the two rotor legs as we're looking through the stator. Okay, so here is often we'll call this the deep set rotor bar, and the second one we'll call the shallow rotor bar. But two cages, two rotor bars, and inductances and reactances. And again, it's a steady state circuit model. Now, different from that model and of greater detail, we have a flux model that simulates a lot more. It simulates the time constant effects of the rotor. Yes, there's a time constant in the rotor bars. Because they're surrounded by so much laminated iron, you can have time constants between a half up to a second. That's the time it takes current to actually build up in those solid rotor bars. Our model is a symmetrical model, just like an induction motor rotor is. The slip is automatically included in the model. We include saturation on both of the axes. So complete saturation detail, and on top of that, we simulate the full dynamic behavior from overspeed to standstill and under all voltage and frequency conditions. So if you have a low frequency condition, will the model perform and act the way it should? Yes, it will. You're guaranteed that if you're doing even a load shedding study, no matter what you're performing, the motor will perform. If it has to do a fast bus transfer and you're looking at transient torques, it'll be able to do that as well. And that's what we decided. That's really what we wanted, is we didn't want to have to make guesses on whether we had enough detail. Now that model looks like this. We're not going to go into detail, and that may even be hard to see on your screen over the webinar, but this is just to give you an idea that indeed there is detail in the model simulating the saturation effect, simulating imaginary and real axis components, simulating XL, X double prime, X prime, X, all of these values, T prime D0, T double prime D0, all of these components that you typically see in a synchronous machine are being simulated in detail here for the model. The other component that's needed is the inertia component. So we have a torque difference between the electrical torque on the air gap and that of the load. That will go into this real simple inertia equations, which is very standard for all rotating machinery, 1/2HS, and we generate a speed on the output. So again, the flux model is preferred. Unfortunately, now we have this data that we have to come up with. What data? This data, you know, RA, XL, X, X prime, X double prime. You'll never find that information, really, for an induction motor over its full range of operation. I've seen values like this in motor data sheets for like one particular loading level or one particular speed point. But to represent the motor over its full speed range of operation, no, you won't find these values typically. But so what do we do then, I guess? Well, we have to find them. We have to create them. And what we have done with the software is we have created a tool for you that, using standard information that you can get on an induction motor, you can create those parameters and you don't even really have to think about them. They're automatically calculated and returned into the motor. You notice if I were to bring up easy power here and I would look at the motor data in the dialog, you'll notice that they are here. RA, XL, X, X prime, X double prime. Yep, they're all here. And these have to be figured out if we want to be able to run the simulation. So we want that. That's going to be hard to get, but we are going to give you the tool to do it, and it's actually a very simple and fast process. That's the really great thing, is we've made this really easy to do, so that we don't have to ask, hey, will my simulation include voltage source effects? What if the voltage dips? Well, you know, what if the voltage goes high? Will that be impacting on my motor simulation? How about flux buildup in the rotor? Is that being included? The time constants in the rotor. Does my simulation, you know, the time constant buildup in the rotor affects how much torque you get out of the motor. It's an interesting thing. Often if a motor starts really fast and it doesn't have time to build up the currents in the rotor bars, you'll actually get less torque out of the motor. Does my simulation handle over and under frequency conditions? I'm simulating a load shed. Well, will it handle it? This model will. Does my simulation include transient torque effects on fast reclosing? In other words, I open the motor and I close it back in really fast because I want to do a fast bus transfer like in a nuclear facility, because I had a main outage and I want my auxiliary bus to be switched into my motors as quick as possible so I don't lose pumping. I don't lose my pumping action. So I don't lose water cooling. So what are these data values that you need to do a parameter derivation? All right, let's look at them. You're going to need to get a torque versus speed curve. Rated horsepower, voltage, power factor, efficiency, slip, and RPM. The starting current, starting torque, and starting power factor. And the pull-out torque, the combined motor and load inertia. Now, the torque versus speed curve, I think on large motors especially, we'll be able to get this with pretty much ease. The rest of these at rated conditions should be very easy to get a hold of. Starting current, starting torque, you can pull those off the torque versus speed curve because often the current curve is included right along with the torque curve. Starting power factor, that's one of the harder ones. For large motors, you'll see this value supplied pretty easily. But for smaller 40-volt motors, I've often found that this is a missing number that, that manufacturers don't have. And I have a way to come up with an estimate of that number. And I'll show that to you later. Pull-out torque, again, can be read off the torque versus speed curve. And finally, combined motor and load inertia. Yes. Hopefully you can get that, because in all reality, the length of your motor start time is directly impacted by this. If you have inertia of 0.5, an H value, kilowatt second per kVA, if it's 0.5, and your motor starts in 2 seconds, if you double it to 1, your motor start time will double. It just takes longer to spin the inertia and get it going. It's a complete linear effect going on for starting your motor. Very critical, critical, combined motor and load inertia. Not just the motor, not just the load independently, but combined. You have to add them together. And I have an equation for that for you that you can use later. Okay, so now that we have these values, what is our method? And our method will be straightforward. It'll be like this. Gather this information that we just looked at, your manufacturer's data. That's your task. Enter the data into the software. Okay, you have a specification tab and you have some numbers to enter in the dynamic stability tab. It's your task to enter that data in. Then use the Easy Power tool that I'm going to point out to you that's hiding. Well, it's not really hiding, but you may not have noticed it in the motor data dialog in the stability tab. It's there. It's ready to use. Use that tool to match the torque versus speed curve and rated and starting conditions. That's going to be your task, but you'll find it's actually rather simple and easy to do. Next, use equations to convert from circuit to flux parameters, and we do that for you. As soon as you hit the OK button in the Easy Power derivation tool, it'll automatically convert to flux parameters and store them in the dialog for you. So we'll do this for you, and we'll make this step 3 so easy for you. You'll probably get a derivation done in under a minute once you get used to it. The first time we may take a few minutes, but once you start doing these over and over again, you should find yourself flying through them pretty fast. Now, the derivation tool was developed for a couple reasons, and obviously it helped us understand a lot of the concepts and the links between steady state and the steady state model and the flux model. But mostly, I would say mostly, it was built out of the frustration with using spreadsheet techniques to try and figure out how to generate a torque speed curve by hand modifying each of the parameters of the circuit model. It just took forever, and I can remember spending up to half a day on motors when I was back at my previous employ in upstate New York. It really did take a while, and so out of that frustration, the derivation tool has been made for you, and again, it's in the motor data dialog. And We want this with the greatest level of detail and also the easiest to use at the same time. That's the power in Easy Power. You'd be surprised how much is behind that, just that one small tool and what it's doing for you to be able to generate those parameters for you. So let's continue and jump right into our parameter derivation. And I've got an example for us to do. And but first, let's just go through it again. Data specified, that slide that we showed earlier, that's the data that you're going to need. Through experience, we've discovered that this set of data is the maximum number of constraints that you can place on a double cage model. You can't put any more. If you do, you won't be able to get a solution. We want you to match the entire torque versus speed curve if you can, but we find that that rarely happens. And the reason why is because manufacturers, this last point here, manufacturers' data is often in error or inconsistent, and it's often hand modified to meet guaranteed torque requirements for their sales literature instead of actually being what the motor does. So there's some issues here, and often you'll find that the peak torque, the pull-out torque, is, you really need to put a higher value in there. Let it be a higher value to get your error down into the 5 to 7% area. And we want you to have the rated starting and running conditions to have an error of 5%. And you'll see that. There's a nice little bar chart for you to see this. Now, if you don't have the starting power factor, here's an equation that you can use to estimate it, assuming that you can't get it from the manufacturers. And here's a few more items, for you, some suggested ranges of values for starting current, torque, power factor, efficiency. And if you can't find data, definitely go to the library in Easy Power. It's there for you. All of the data is there. Again, you have a motor. You double click. You go here. You can just automatically load a motor in and see what kind of values are here for amps, slip, starting torque, starting current. You can automatically pull those out right from the spreadsheet here. And let's figure out where that went. Here we go, PowerPoints. Also, inertia. I mentioned that's one of the most critical factors for your starting time. And you'll have to convert the data that's been supplied in pound-feet squared. It's typically called WK squared. I've also seen it called WR squared. You put it in this equation, and out will pop the inertia constant H in kilowatt second per kVA. If you have a metric motor and the inertia is in kilogram meter squared, then use this second equation. So here's a motor. We're going to start with this small 15 horsepower motor. And this is the data sheet. It might be hard to read for you over the webinar, and I understand. And so what I've done is I've tabulated these numbers in 1 or 2 slides down. Okay, so here's the torque versus speed curve that goes with it. The torque versus speed curve is this one right here. You've probably seen some of these before. And the tabulation of our data for this motor is here. And I went ahead and just did this for you. And it'll be in the slides that you get a copy of. We'll send out a PDF to everyone here at the webinar. And we'll send that to the email that you've supplied when you logged in. Okay, so let's do it. I'm going to put these slides over here on the right-hand side so I can still see these values. And I'm going to start with a new case. No, that's not what I want. Come on. Webinar example 1. So here we go. I went ahead and built a small system with 2 buses and a transformer. And we have our 15 horsepower motor. Now, I've actually already done this one for you, but let's just do it all over again, okay? Notice it already has the stability data in it. But let's start over. This is a 460 volt motor. It's 15 horsepower. The RPM, the rated synchronous RPM is 3,600. Its power factor is 0.907, that's correct, and its efficiency is 0.923. Now, whenever you put a motor in for the first time, remember, when you hit the OK button, you'll often get an error that, hey, you didn't finish everything in the data entry. And that'll be this item on the short circuit tab. The X over R ratio is often blank, and it'll have a little red exclamation point. And when you hit the calculate button, it'll fill that value in for you. Next, go to the stability tab. And when you appear, or you've come in here the first time, it'll appear to be unchecked. You will want to check it. And the first thing that we're going to want to do is we want to supply seed data for our derivation. In other words, we don't want to start with nothing, because you don't know what x prime, x double prime, where do you begin? It's got to start somewhere. And so we've already done a host of derivations in here on motors. But what I suggest, just grab the generic one, okay? Just go quick, right here, generic, standard induction, boom, click the library button to import it, and up pops that question again, overwrite power factor and efficiency in the spec tab. This time you will say no. And the reason why is we just entered it. We don't want to overwrite it with values from the library. We're just using the library for seed information now. Now we're going to derive our motor. So we're going to say no in this case. These values in gray match the spec tab, so they just are brought right over. The rated slip, if you look over on the right-hand side, is 0.0194. Next item, starting torque, is 1.9 per unit. The starting current is 6.96 per unit, and the starting power factor is 0.35 per unit. Pull-out torque is 3.02. Boom, we're done. Now we have entered in these values, and we're going to leave the rest of the seed data here. We're just going to leave it alone. Now we're going to do our derivation. That's this tool, this button right here that looks like a small plot next to the model. You click on that, and you're brought into the parameter derivation tool. Now again, I did this once before, so I'm going to clear it and start over again. As soon as you enter, you want to bring in a scanned image of the torque speed curve that's been nicely corrected so it's square, good. You want it as good as possible. And that's right here for me. That's this induction motor 1 derivation. Now, notice that to import it, you need to supply maximum percent torque and also the speed axis direction. Now I have this plot over here on the other side in another window here, another screen. Let me bring it up just a second. Yes. Okay, so what I want to do is bring this over and just show it to you again. Okay, this is what we imported. It's got the dialogue over it, and it hasn't really imported it yet. So this is the image we're going to be importing, and I've already determined the maximum torque for you. I took 120 pound-feet squared and divided it by 22.5 to get this nice 540.5% for you. Okay, so maximum torque in percent on the plot scale is 540.5. And if you look at the plot again, we are going from 0 speed to 100% speed. So it's 0 to 100. Often these curves are flipped. It goes like this, the curve goes up and then it goes down. So your starting condition is here, 0 speed, and it's flipped. For that condition, you'd choose the opposite. So yes, 0 to 100%. There it is. There's our image. Now, what you need to do to begin your digitizing effort is to take the red box in the corners and drag it to the extents of the plot. And that would be here and here. There we go. That's pretty good. The next thing that we want to do is we want to start digitizing. And we click on the curve. And you don't need a lot of these because it splines between them. And the ones that aren't lining up really well, we'll just move around a bit. That looks pretty good. That looks good. If you make a mistake, let's say you add another point, like up here, you just hit undo. Yeah, it'll undo it for you. You can start all over again if you'd like to as well. You just clear and just bring in the image again and start over. Notice all the digitized values are over here on the left. If you want to copy them and paste them into a spreadsheet, you're welcome to. And now that we've done this, we are going to go to step 2. And I just point out, this is not for equations or any type of math. This is just a picture. So just make it look close. And what we're going to do next is take the curve. Oh, this didn't come out very well. Look at that. That last point's kind of straight up like that. Yeah, okay. So let's kind of fix that. Let's bring that over here. That was a nice little catch. There we go. That's a little smoother now. Now in step 2, the goal is to match the blue curve with the orange curve. And I'll show you how to do that. First, I want to point something out. Number 1, we did a good job at digitizing because the black diamonds represent running and starting torque. And they had better line up right at the ends and on top of the blue curve at 100% torque. Yes, rated 100% torque, and at the starting torque condition. And our digitizing looks good. Next thing is, this is the bar chart of errors in rated current, rated power factor, starting torque, starting current, and starting power factor. We want these to be 5-7% maximum if we can get them there, okay? Next, the way you move the orange curve is by dragging the orange gravity points. The black ones don't move. You click on them, nothing will happen. If you click on the orange gravity points, I'm clicking and holding and dragging. You will notice, let me just stop that from updating over there. You will notice that it will move the curve. And if it were me, I would probably stop right there. One thing to remember, this peak curve, again, for this blue digitized curve, that's often a guaranteed pullout torque, not what the actual motor does. You may find that it's higher in reality. Let's stop right there. I think that's a pretty good match. Close enough. This up part is very hard to match. That's not simulated. That type of effect, I believe, is from skin effect, resistant skin effect in the rotor bars. And that's not being simulated in our motor at all. You can try and do that by pulling up and pulling down. But again, it's typically a pretty hard thing to do. Or maybe pulling down here, because the gravity point is pulling up itself. Again, it's just a really difficult thing to match. So let's just come back down. Let's call that a pretty good match right there. I like that one. Okay, I'm going to hit OK, and when I do, it will automatically convert values into flux parameters and load them in right here. Very nice. We're ready to go. Hit the OK button, and of course, hit save because we don't want to lose anything. And now we're ready to start our motor. And notice we now have the symbol for the induction motor data. All right, let's do an actual analysis. Let's go into dynamic stability focus. And just in case, yes, that is set correctly. I set my simulation time step 10 lower just because I noticed that the, I can show you this here, the subtransient time constant was really low, 0.00103 seconds. That's really fast. And you'll find that this may cause your simulation to go numerical. I mean, we recover from it nicely in this dynamic stability package. We'll just tell you, hey, you have numerical issues, you need to lower your time step. And so all you do is go in, options, lower your time step. It'll take the simulation a little longer to run, but you have to cover for this condition. When you're starting motors, that's one thing you have to understand about any type of transient motor starting dynamic stability is you have to have a very short time step because the frequencies in the rotor are 60 hertz under starting conditions. So go into stability, come over here, see our motor initial condition. Yes, it's ready to go. Open and resolve because we need to have it off before we start. And we double click and we start. Really fast start time here. A couple other things to notice. This glitch here on the current, this is due to, I'm going to zoom in to look at that. All you have to do is click with the left mouse, drag to the right, and now you've zoomed in. This is like a numerical artifact due to the modeling method on the inside of the rotor model. And it's, I could go into a lot of detail on it, don't really need to, but just understand that it basically has almost no energy in it. And so it really doesn't affect your simulation at all. It's an artifact due to that the rotor equations are simulating the actual transient currents kind of in a DC method versus the AC RMS on the outside of the model. You're kind of mixing two domains when you do that. And this is well known and well understood in that area. If you want to zoom back out, click on the zoom out full. This is a very fast motor start. And like I said, you know, I mean, this is like way under 1 second. We can make this longer simply by increasing our inertia. So we come down to the inertia, which is, 0.4. Excuse me, that is yeah. Let's set it up to 2, and you'll see a significantly increased starting time, almost 4 times longer. Boom. There we go. Now we have the motor taking significantly longer to start. Again, we see the voltage dip, which is very minor here. Very minor. We see the starting current up around 6.9. I'll drag this over here. See them together. You know, around 6.97, which is right out of our data. And we don't see really any voltage dip at all on this. Notice the interesting. Notice the voltage is 1027. It's a 460 volt motor on a 480 volt bus. And what you're plotting here is the motor voltage, not the bus voltage. You plot bus voltage, it'll show up at 1 per unit and then dip slightly. Okay? But here, we're seeing it on a 460 volt base. And that is true. If there was nothing on that bus before and this is a very light load, your voltage is going to be roughly, you know, 1 per unit, which is 480 volts, not 460. That's a nice little interesting thing to note. Okay, so we've done complete derivation all the way to bringing the data into the model, coming into the dynamic stability focus. We've done a motor start. We've shown how to maybe add some more plots. Look at that, bus voltage on bus 2. It's already there for us. So if we start the motor again, there's our bus voltage. Yep, there's that dip. Dipping down to 0.98 at the lowest point. And what I'd like to do now that we've gotten through the whole derivation method, showed you how to do that, is I'd like to show some other sideline effects that happen when you're doing motor starting. A lot of times the focus is completely on the motor at hand. What is the motor doing? How low is the voltage going? Is the motor starting? How long did it take the motor to start? Often infrequently for motor starts, do people really concern themselves with the whole rest of the system? What is everything else doing? How are all the other pieces of equipment? It's when you get to the really large motors that's when that becomes a concern and people start taking notice. They want to know, hey, am I going to trip when I start that motor? How low is the voltage going to go? If it goes too low, I might drop out some other contactors on some other motors, and I definitely don't want to do that. And so to look at that, I'm going to close this case here. We've done a good derivation here. And yes, let's go ahead and save it. Now I'm going to open up DS example 2. This is a case, again, that comes with your installation, and you can use it. You can investigate with it, play with it, try new things with it, modify it, do whatever you'd like with it. And but it's a very simple system. Has a co-generator, has a utility tie over here, a main 13.8 kV bus stepping down to a 4160 volt motor control center, and a 480 volt MCC, actually 2 of them. It also has a standby generator hooked up through an automatic transfer switch. It has under frequency protection and overcurrent protection. So what would happen if we were to start this 3,500 horsepower motor, M2? We are already in here in the dynamic stability focus. So all we have to do is open and resolve to prepare it, get it offline, and then close by double click action. And here we see, very interesting, the motor terminal voltage dips down to, let me drag this over here for us, dips down to 83.7, 83.7, yes, roughly, %. Starting current is up around 5.3 per unit. And the motor starting in about, that's about 1 second. Yes, starting here at 1, right there, going to roughly 1.9, which is roughly a second for the start. Now, some interesting things. Often, the message log is kind of ignored in transient motor starting and dynamic stability. You want to see the plot. You want to see what the motor start is doing. But there's a reason why this third window is down here. And let me take it and bring it up for you. In this window, we see that we have a complete log of what happened during the initialization. And I'm not going to go into detail about this. This says D state settled for all models. That means it passes and I'm all good. Now, I would just note that every time you do a double click action, in reality, we run a script. We write it behind the scenes and then we run it through the scripting engine. The scripting tool, which will be discussed in a later webinar, gives you a lot of powerful features for where you can basically do a cascade start of motors. But for now, again, all we're looking at is the single double-click actions done on breakers. So what happens is we write a script and then we run it. So remember, the delay time was 1, the run time was 6. So what happens? We run to 1 second, don't do anything. Then we close the device, which is that fuse switch that was up there. And in the runtime, the motor says, oh, hey, I'm starting now. Someone asked me to start. And the script then runs to 6 seconds. Notice what happens. Relay picked up on overcurrent, 2 of them, R1 and R7. Relay 1 reset at 0.8% travel, now traveling back. Relay 7 reset at 3.9% travel. So we did an okay job on these relays and setting their pickup settings and where they're going to trip. But if these weren't set so well, you could definitely see by running a motor start simulation, you can determine whether you're going to trip protective devices or not. Now, if you have the power protector feature and you've done a whole bunch of work preparing for short circuit and coordination and arc flash studies, you have them all. You don't have to do this again. They're all entered. All you have to do now is use them. That's one of the powerful features of dynamic stability and motor starting. is you can now use all those protective devices for real-time simulations, not just for coordination in Arc Flash. Okay, you can get more. You get more for your money now out of that. So valuable information here. Notice a nice trick. If you're in here, you have these 3 windows showing, you hit F8 and it puts them all back in order. Another trick, the bottom right-hand corner here of the main one-line window, drag it and they follow. So you can quickly resize your windows. So we started this large motor. Wow, I wonder, when I started this motor, what happened to the motors on this bus? Right here. I just happen to have already predefined these plots. So in this plot, let me grow it for us. There we go. In this plot, we have the bus voltage for MCC3. Boom, right here. You can see that the voltage dips. Then it continues to go down and down as we lose the contribution, that's the help that's coming from M3, 4, and 5. And also, because of this voltage depression, look at the current on M4 increases and goes up during the voltage depression, and then it comes down. Very interesting. It's not a really large increase in current, but it is significant. That's something to definitely understand in your system. If you're ever near the edge of a voltage collapse or something in your system, note, you have voltage depressions like this, you can cause other things to draw more current and thus make it worse. Yeah, it'll just make the voltage depression worse because more current is now being drawn through, for instance, transformer 3 here that feeds MCC3. So that was the last thing I wanted to show you today is, again, we got through from the beginning looking at the data that's necessary, looking at the models and the reason why we wanted the full detailed flux model. From the data, then we did a parameter derivation. And when we got finished with the parameter derivation, we did some nice motor starts and we showed how it's really an important thing. If you have a lot of motors in your system, definitely don't just model the one that you're starting. Go ahead, do the best you can on gathering information and data. Yes, and put the data in all those other models for all the other motors so that when you're starting the one, you get the effect of all the others because your voltage will go lower because of the dynamic effects of those other motors as they draw more current during the voltage depression. Well, I want to thank you for joining me today, and I wish all of you the best of luck in doing your motor simulations, and our tech support team here at Easy Power is more than glad to help you out with your motor simulations. And if they can't help you, then most likely, if no one's there helping out with motors, you'll be directed towards me to help you. And since I'm the person who actually authored the dynamic stability package, coded it, specified it, and put all of the models that are presently in there. Yep. So thank you again, and have yourself a great week. Thanks. Goodbye.